In this video, we'll be exploring the EUV and X-ray tool on Predictive Science's new MHDweb 2.0. This tutorial is part 9 of a 12-part series that is designed to guide users through this website's data visualization tools. Once again, if you've not done so already, I recommend reviewing part 1 of this series. It covers in greater detail the website's architecture, general visualization workflow, and the mass run database. So with that being said, to get started with EUV plotting, navigate to the MHDweb landing page. That is predsci.com/MHDweb2 and click on the EUV and X-ray button here. And I'm going to go ahead and select a more recent steady state Carrington rotation run, Carrington rotation 2290. And if the plot that you're presented with is a little bit darker than you're expecting, you can just select this reset values here and it'll apply the default values for the EUV and X-ray tool. So this page's architecture shares a few similarities with the white light tool, which is covered in part 7 of this tutorial series. Both tools allow two distinct approaches for generating plots. The first, which is the default approach, is by toggling the custom view option off and selecting a filter from the provided drop-down menu here. So there are 7 distinct EUV imagers that are represented in this drop-down here, including, among others, Solar Dynamics Observatory's AIA, their Atmospheric Imaging Assembly, COHO's EIT, or Extreme Ultraviolet Imaging Telescope, and Solar Orbiter's UI and FSI. Each of these instruments offer a selection of different wavelengths for which EUV images can be generated. So with the custom view off, the field of view for these filters are fixed. They're determined by the EUV instruments themselves. And then for both custom view on and off, the color maps for the filters are determined by the EUV instruments. So the spacecraft ephemeris, however, is determined by the time of interest that is supplied in your simulation widget. This timestamp is used to query, as in other tools, Jet Propulsion Laboratory's Horizons API, which fetches the instrument's positional coordinates. As I've mentioned in other comparison tools, spacecraft mapping, time series comparisons, one thing to keep in mind is the respective time frame for these missions. So certain mass runs will not be compatible with an instrument selection simply because the run time range does not intersect with the mission time range. So you can find further documentation on Ephemeris availability at the JPL Horizons link that I will provide in the video description below. Another thing to keep in mind, particularly when selecting your mass run type, is that polytropic models don't possess the same temperature fidelity that is inherent in thermodynamic models. This has to do with the fact that polytropic solutions don't solve for the energy terms in the lower solar corona that are particularly applicable to EUV rendering. Instead, we set the coronal densities and temperatures as fixed boundary conditions. As a result, the solutions possess little variance in these terms, yielding somewhat smooth EUV plots. And I can demonstrate this by selecting the simulation database. And for Carrington rotation 2290, I'll select the polytropic version. And you'll see here sort of what I was talking about with this consideration. And as you can see, if you've selected a polytropic solution in the mass run database, the EUV plot will contain a warning, which you can see right up here, that non-thermodynamic model selected, and that this can lead to strange results. So I'm going to return to the Thermo 2 for Carrington rotation 2290. As we covered in the white light tool, in the data widget, this allows you to apply certain data transformations to the plot that you're viewing, including scaling it by some radial power, applying a logarithmic transformation, and radially scaling the plot using the supply vignette toggle. Now, opposed to the white light tool, where there is a series of predefined vignetting functions that you can apply to the plot, this toggle actually creates a bespoke radial filter for the given spacecraft wavelength and filter function that you are examining. So if I toggle this on, sort of effectively almost flattens the color spectrum of this image. I'm going to toggle that off. And also, just for the purposes of demonstration, we'll examine a couple of these other instruments. So we'll look at EIT's 171. And we can take a look at FSI's 304. Now, as you can see, this tool is a fairly data-intensive application on the back end, and so these plots will take a little bit longer to generate. And as I mentioned before, you can supply the orientation as well as the simulation Rmin and Rmax, which will show up on the plot. So this is showing the P angle, which for this one is 0 degrees. This green line is the radial inner boundary, and the red line would be the radial outer boundary. However, for the EUV plots, generally speaking, the field of view is close enough that you're not really going to be seeing the model outer boundary. So I'm going to toggle these back off, and then we can go over the second approach for constructing EUV plots, which is by toggling the custom view switch on. So this feature enables more advanced set of specifications for plotting an EUV image, allows the user to control the position of the observer, as well as custom fields of view, as well as the other options that are available to both approaches, for example, color bar scaling and data transformations. Now, since the custom view allows you to specify Ephemeris directly, the plots are no longer constrained by an instrument's mission time range. So this will allow you to construct EUV plots for quote-unquote what-if scenarios. In other words, utilizing a particular instrument's filter to generate EUV data for any time at any position. For example, if the mass run that you are evaluating lies before solar orbiter's launch, with the custom view functionality, you'd be able to examine FSI imaging if SOLO had been operational. Or another example of this is for stereo behind. So we lost contact with the spacecraft in roughly 2016, if I'm not mistaken. So in theory, what we could do is from this drop-down menu, select EUVI for stereo behind, let's say 195 angstrom. And what this plot now shows is, although stereo behind is no longer we're no longer able to communicate with stereo behind, especially not for October 30th of 2024. We could examine a sort of hypothetical plot for what it would be seen at a specified ephemeris here. So with that being said, I'm going to return to AIA 171, and we'll go on to examine the view widget in a little bit more detail. So much of this will be review if you've already viewed our white light tool tutorial, but by default, a field of view is supplied. Effectively, what this is doing is setting the x-axis and y-axis symmetrically about the origin or sun center with the provided degrees here. However, if you want to examine a sort of non-regular bespoke view, all you have to do is simply delete this field, and you'll be supplied with specific ranges for your x-axis and y-axis. So if I expand these x-axis and y-axis drop-downs, you can see the min and max values here. If no value is supplied, we've chosen a sort of arbitrary degree value as a default, namely 0.53 degrees. However, if I wanted to examine a non-symmetrical field of view, I could, for example, for the x-axis put 0 degrees. I would show you a plot between 0 and 0.53. And I can extend that out to, let's say, 2 degrees. Now this is in degrees of line of sight. And alternatively, if I wanted to examine, let's say, just this lower half of the plot, I could specify the max value as 0 for the y-axis, and now we'd see just this sort of lower half here. And as many of these options are sort of an extended functionality from the white light tool, you can provide view limits that omit the sun center, but by toggling this show sun center switch at the bottom, the plot will extend the x and y axis to include the origin. So let's say that I'm examining my x-axis from, let's say, 0.1 to 1 degree. And for the y-axis, I'll move this up a little bit, say 0.2 degrees. I just want to wait a moment for the plot to populate these changes. What I can do from here is toggle this Show Sun Center switch, and it will extend the x-axis and y-axis to include the origin right up here. As you can see, the View widget allows you to define highly customizable fields of view. The only constraint on these view limits is that a given field of view shouldn't exceed 5 degrees from the sun center, a constraint which is supplied due to the sort of diminishing returns on meaningful data values beyond these extremes, especially when considering the processing power to compute such wide fields of view. And just to illustrate this, take a look at what a field of view of 5 degrees looks like for AIA 171. Now, as I've mentioned in other tutorials, you can download the image that you're viewing with this button right here, and similar to the white light tool, you can download the underlying data that is used to generate this image with this Download Fits Data button in your upper right-hand corner. And with that being said, that concludes this overview of the EUV and X-ray tool on Predictive Science's MHDweb 2.0. The next video in this series will go on to explore the EUV Imagers and Comparisons tool. If you have any questions, comments, or concerns, please leave a comment below, and thanks for watching.